Welcome everyone to the M-Cubed seminar, and I'm pleased to introduce Cristina Sgattoni. She obtained her PhD in mathematics from the University of Florence in 2020, where she worked on numerical optimization methods. She then joined the Institute of Applied Mathematics, or IAC, of the National Research Council of Italy, CNR. Her work contributed to the preparatory activities of the European Space Agency Forum satellite mission. Since 2024, Cristina has been a research scientist at the Institute of Bioeconomy, or IBE, of the CNR. Her research focuses on exploiting future forum measurements for data assimilation in numerical weather prediction models, and on the application of artificial intelligence techniques to direct and inverse rate of transfer models in collaboration with Emory University in Atlanta. She also coordinates an international network of early career researchers working on forum and related atmospheric remote sensing topics across Europe, the United States, and Canada. Welcome.
Good afternoon. Thank you for the introduction. I am Cristina, and I'm a scientist at the CNR in Florence. And today I'm going to talk to you about the European Space Agency Mission Forum and our related work, in particular involving AI techniques for retrieval methods and also data assimilation. So this presentation is divided in three main parts. In the first part, I'm going to give you a brief introduction about the forum mission in general. I'm a mathematician, so I'm not very into the technical details of the instruments, but I'll do my best to explain the architecture in general. And the second part is about the retrieval algorithms. That is my main focus. And in particular, I will present two different methodologies that are separated. One works in clear sky conditions, and the other one is a more general and works in all sky conditions. And at the end, I'm going to talk about an algorithm that we are developing and testing in order to select the most important information in our measurements in order to assimilate them in the future in NWP models. So let's start. So FORUM stands for Far Infrared Understanding, Outgoing, Radiation and Monitoring, and is the 9th Earth Explorer mission of the European Space Agency. As you probably already know, the Earth Explorer missions are different from the bigger ones that are the Copernicus missions and so on. So we have a lower budget with respect to the Copernicus missions, and in general, the Earth Explorer are scientific missions. The team involved in the missions is quite big. There are institutes all over Europe, and the lead investigator is Luca Palchetti, that is in my lab at CNR in Florence. And in this slide, you can see on the left the official website of Forum, and where you can find all the information that you need if you are interested. And in the right part, you can see a picture of a part of the team, because we have a lot of workshops and meetings all around Europe, and this is related to the second forum workshop in Leicester, UK. So FORUM, as already said, stands for Far Infrared Outgoing Radiation Understanding and Monitoring. And the scientific aim of the mission is to measure the Earth's top of the atmosphere emission spectrum from 100 to 1,600 centimeters to the -1. And so the aim is to fill the gap in the far infrared part of the spectrum that has never been observed systematically and spectrally resolved from space in its entirely, and integrating the observation with, for example, CRIS, YASI, HIRS, and so on. So the idea is that the satellite will fly in loose formation with a METOP SG hosting YASI and G. So the goal is that the distance between the orbit ground tracks will be less than 100 kilometers, and the time lag between the two satellites will be less than 1 minute. In this figure, you can see the spectral regions covered by the forum instruments that are the first two lines, and the YASI corresponding to the third and fourth row. forum, on board of the satellite, there will be two different instruments, the so-called FSI, that is a Fourier transform spectrometer, that will measure the radiation, the upwelling spectral radiance in the spectral region that I already said. And the spectral, anapodized spectral resolution will be 0.5 centimeters to the minus 1, with a spectral sampling of 0.36 centimeters to the minus 1, with a high radiometric accuracy. The second instrument is a forum embedded imager that will measure only a channel, and it will be useful for characterize the homogeneity of the scene. This kind of imager is a lower budget with respect to the ESA one, and is not good, for example, for cloud detection. So I think that you all already know why far infrared is important. But let's summarize. In general, it contributes from 1/3 to 1/4 of the greenhouse effect in clear sky conditions, and it reaches 50% when we consider also clouds. The far infrared is also dominated by the water vapor rotational bands, so it's highly sensitive to lower troposphere, lower stratosphere humidity. And the far infrared emission is observable particularly in the dry region like Antarctic and Arctic. And so it's very important in order to understand the polar warming. And another objectives are the cirrus clouds that in current models are very poorly constrained, and the current models are also inconsistent in the middle infrared and the far infrared. And finally, the lack of the observations also prevents accurate cloud radiation feedback simulations. So what we want to do is to provide the first globally spectrally resolved far infrared database, and also constrain water vapor, clouds, microphysics, surface emissivity, and reduce the uncertainties in climate projections, and also support policy decision. In this picture, you can see an example of the forum spectrum. In particular, you can see the radiance in black, and the different spectral regions are highlighted with different colors. And you can see, for example, denoted by the red color, the so-called atmospheric windows, where the atmosphere is transparent, and so you can see the surface properties from there. In fact, if you look at the spectrum overlaps the two dotted lines that are the Planck functions of a black body emitting at the temperature of the surface. And on the contrary, for example, the yellow region is the CO2 band that is very opaque, and in this case, the spectrum overlaps the Planck function corresponding to a black body emitting at the temperature of the tropopause that is colder and is higher in the atmospheric layers. And so this is a scenario, sorry, I forgot to say it, that is related to a mid-latitude scenarios. The launch will be hopefully in 2027. Forum will fly in a polar orbit, sun-synchronous, and the repeat cycle is 29 days with 412 orbits, and the satellite will be a nadir viewing satellite. And the ground pixels are circular with 15 kilometers of diameter, and the distance between two measured pixels will be 100 kilometers. And the expected lifetime is about 5 years. In our team, we developed an end-to-end simulator in order to simulate all the process, the entire measurement acquisition process, and also propagate all the sources of discrepancies that may arise in operational conditions. And so we evaluate the impact of level 1 and level 2 products. And we use the radiative transfer models LBL RTM plus LBL DIS, and then we simulate the radiance reaching the instrument with measurement distortion, like the instrumental response function, the noise equivalent spectral radiance, and the absolute radiometric accuracy that you can see here in the picture. You can see in blue and black the ones related to EASI, and red and yellow the ones related to Forum. So if you want to know something more about it, you can ask me. And you can also interrupt me during the presentation if you want. And as already presented, I'm happy to organize and lead this group of people that are early career scientists. The group is composed of 50 members from all over Europe, US, and Canada. And we have monthly presentations, journal clubs, workshops. And we already did a lot of workshops virtually and one in presence. In this picture, you can see some of the people joining the group in Vienna and Bologna. And we have also, in the group, people that are involved in the so-called twin missions, that are the PREFIRE mission from NASA and the HAWK mission from the Canadian Space Agency. So let's move now on to the second part of the presentation. So my main topic is the retrieval algorithm starting from radiance measurements. And we are trying to use AI techniques in order to speed up the inversion process. This is a joint work with Emory University in Atlanta and University of Bologna and some other institutes of CNR in Italy. So as you all probably know, in this field, we refer to direct problem as the problem of finding the atmospheric status vector, X, starting from measured spectrum Y, and using the capital F, that is the forward model, known as forward model. And the inverse problem instead consists in finding the measured the parameter vector known as retrieval vector, starting from the measured spectrum Y, minimizing the difference in norm. As you all know, this problem is very ill-conditioned. Our target variables are surface temperature, water vapor, ozone surface emissivity, and some cloud parameters. And so we try to retrieve all the atmospheric quantities in atmospheric layers. So we retrieve vectors for temperature, water vapor, and ozone, and the spectral emissivity in a particular spectral range, the same forum. So as you all already know, this problem is a very ill-conditioned problem, and the way in which we solve it is to formulate the problem as a Bayesian inference problem, and then solve it using the optimal estimation method that consists in minimizing the quantity that you can see in the middle of the slide. And the minimization algorithm that usually we use is Gauss-Newton plus Levenberg-Marquardt technique that helps in the inversion and numerical stability of the method. And I'm not going into the details, but if you want to ask me, I'm happy to answer. So classical retrieval methods explicitly rely on the use of the forward model and also iteration minimization procedures. So they are computationally quite expensive, and that's why we would like to use machine learning techniques in order to speed up the inversion. And machine learning techniques should be so fast and should work for real-time retrieval. So that's our objective. And this kind of methods heavily depends on the choice of the databases, the training sets, that should capture the variability of the atmosphere, of the clouds condition, and should be representative. So let's start with the first method that we developed. Is a clear sky method, and is called the physics-aware data-driven method. You will see why. And this paper has been just published in Inverse Problems. So the method scheme is the following. It's composed of 3 different phases. The first phase is a completely data-driven phase in which we approximate the radiative transfer inverse operator using a linear operator that is trained on a database of forum simulated measurements. This is completely data-driven. The second phase, in the second phase, we incorporate some information from physics into the data-driven solution. So it's a sort of regularization technique. And in the last phase, we use another machine learning technique, very simple, to decide the weight of the regularization. So let's start with the first one. So what we do is to, as I already said, approximate the inverse operator with a linear operator that we call Z. And our training set is composed of almost 2,000 cases computed with LBL-RTM. And so we collect all the atmospheric scenarios in the matrix X and the corresponding forum spectra in matrix Y. And then our goal is to minimize the difference between X minus ZY in Frobenius norm. And with very simple calculations, we can obtain that the optimal minimizer, the minimizer that we indicate with Z hat, is the product between X and Y plus, where Y plus is the Moore and Perrow pseudo-inverse of Y. So in this way, we can use this operator in order to compute the data-driven solution that we indicate with X hat, starting from the measurements Y. In this slide, you can see some results. In particular, the mean signed errors in blue and the mean unsigned errors in orange. This is an average result on the entire test set of about 400 cases. And in order, you can see results related to temperature, water vapor, ozone, and surface spectral emissivity. And what we can say, starting from this picture, is that our method is unbiased. And so it's globally, let's say, in average unbiased, but we cannot say anything about the accuracy if we don't look at single cases. So in this picture, you can see plotted the differences between the true values of the profiles and the retrieved profiles for the same variables. And as you can see, we have a lot of oscillations that are unphysical. So that's why we need to add a sort of regularization technique. So we can move onto the second phase, in which we solve a bi-level optimization problem. So the inner problem is the first one, and the outer problem is the second one. So we want to find X lambda that minimizes the first quantity here, in which we have in the first term the solution that we already computed in the previous phase, the data-driven solution, and the second term corresponds to some a priori information from climatology. And then we compute the lambda, that is the weight of the regularization, solving the outer problem in this way. And the minimization technique that we are using is the interior point method. So in this way, we collect a set of regularization parameters that are optimal. And so we can use this set in order to train another network. That's how we jump to the last phase of the method, in which we train a very simple feed-forward neural network in order to automatically compute the weight of the regularization for unseen cases. And the input of the network is simply the difference between the data-driven solution that we already got and the prior information. And the output will be the logarithm of the regularization parameter. And the architecture of the network is very simple. It has like 3 hidden layers with a quite low dimension. In this slide, you can see the results. In particular, we are plotting, again, the mean signed error in bold and the mean unsigned error with dashed lines. And in orange, you can see the data-driven solution, so the one that we obtained from the first phase, and in blue, the final one after the regularization. And in black, we also plotted the prior errors. So as you can see, we managed to solve all the unphysical oscillations, and the solution improved quite a lot. And the results are related to the usual variables, temperature, water vapor, ozone, and emissivity. And this is that was a plot, an average plot on the entire test set. And this is instead a plot referring to a single case in the test set. And here we plot the differences between the true values and the retrieved ones. And again, with the same colors as before. So we also improved the method for single cases, managing to solve all the unphysical oscillations. Finally, in this paper, we also performed chi-square statistics in order to evaluate in order to compare this method with the full physics method. And in this slide, you can see the distribution of the chi-square, in particular the reduced chi-square. And in the first picture, you can see a comparison between our method in blue and the method in our method in orange, and the method in blue is the one in which we compute the solution using only prior information. So, the important fact here to highlight is that our method outperforms using the prior information as alone, without additional informations. And on the lower side, you can see the chi-square distribution instead of the full physics method that is clearly better than our method. So we are not reaching the accuracy of the full physics clearly, but in some way our method is still better than using simply the climatology. And the strength of the method is the computational time. In fact, we take a few seconds for training one, and more seconds for training two, but these are offline stages. And to test the entire solution scheme, we take about 0.05 seconds for one case. So in this time, we can retrieve all the variables in atmospheric layers, surface temperature, and also surface spectral emissivity. So to sum up this part, so we developed an algorithm that works in clear sky. We firstly approximate our inverse operator using a pseudo-inverse. After that, we incorporate some information from physics through a regularization. And then we use an additional machine learning approach to estimate the strength of the regularization. What we want to highlight is that we train all the method in forum simulated measurements using a line-by-line code, the LBL-RTM that I already said. And you can find all the data related to this work in the link in Zenodo.
Cristina?
Yeah?
In that section, is there a way, so you're saying it's much faster, but it doesn't quite, can't compete with the full physics approach. Do you get information on where you might want to use the full physics approach? Like, when is the AI, are there certain situations where the AI method is particularly poor in its solution, so you could make a decision to go with the more expensive method, but still overall save computational time?
Let's say this is an overall result, but we noticed that in some area the results are harder to obtain with respect to other area. For example, in Antarctica region and Arctic region, we noticed that maybe it's better to use the full physics with respect to this one. Yeah, but yeah.
So I'll go similar to that. So it seems that you used a neural network. Did you had chance to look into any other kind of techniques like convolutional neural network, for example?
In the next part, I will show you another kind of architecture that uses autoencoders. Yeah, but I never tried convolutional neural network, but it could be an idea to incorporate to the next method that I'll show you. Yeah. Someone else? Okay. Thank you. So let's move now on to the second method that we developed. This method works in all sky and is called the latent twins framework. Okay, in this study, we used a different database. We collected data at 12, covering the entire globe in January and July 2021, and we collected about 30,000 cases, and we divided the cases in training set for the 85% and test set the remaining 15%. In order to obtain data, we collect profiles, gases from the ERA5 database, CAMS, ED2, and the surface spectral emissivity database by Wang. And then we use a fast radiative transfer code that is called Sigma and is developed in Italy by the University of Basilicata in order to obtain all the simulated radiances, in order also to speed up the creation of the training set, because in all sky, the full physics method will take a lot of time. So before starting the training, we normalized all the data using the min-max normalization between 0 and 1, and then we used the same normalization data also to normalize the test set in order to avoid the so-called inverse crime. And as you probably know, this kind of methods also require that the dimension of the input and the output is fixed. So we do not have problems with radiances, but we have a lot of problems with profiles because the dimension of the profiles depends on where you are on the Earth. So the technique that we are adopting is normalizing the vertical pressure in the interval 0-1, and then interpolate the profiles onto a grid of 70 points equally spaced between 0 and 1. So this is a sort of stretching of the profiles, and in this way we keep the case-specific pressure ranges of the profiles. So in this case, the retrieval variable is bigger because it also includes the red quantities that we added, so the contents, liquid and ice water contents, and the effective particle radius, liquid and ice. And we also modified a bit the input variables. We put in a vector also not only the spectrum, but also the position, so lat-long coordinates, and also the time and the amount of the scan. Okay, as already said, this architecture involves autoencoders. For those of you who are not familiar, autoencoders are very simple neural networks that learns to map its input to the output. And the autoencoder is composed of two parts, as you can see on the left. on the right, sorry. The first part is an encoder that encodes the information in a space that is called the latent space, and the other part is a decoder that tries to reconstruct the original variable starting from the information learned in the latent space. So the key idea of the autoencoder is that the autoencoder should not learn to simply copy the input, but should learn to some key features of the input in order to learn and to reproduce it. So these are the basic bricks that we are using in the architecture. And the architecture is the following. So we use an autoencoder for the retrieval space, for the atmospheric profiles, and another autoencoder on the right for the spectrum space. And in the middle, between the two latent spaces, we use very simple mappings that goes like direct from the spectrum, the compressed spectrum, to the atmospheric vectors and vice versa. And in general, the autoencoders that we are using have like 4 hidden layers with linear plus ReLU activation functions. We use ReLU activation function because it introduces some nonlinearity given the nature of the problem. And instead, as already said, the latent mappings are very simple with only 1 layer. That's the path that we are going to follow in order to invert our problem. So we would like to go from the measurement Y, encode the measurement in the latent space, then use the inverse operator inside the latent spaces, and finally decode the information from the latent space in order to obtain the reconstructed retrieval variables. We did a joint learning on GPU, so we learned all these 4 networks at the same time with a batch learning on about 10,000 epochs and using the Adam optimization algorithm and a learning rate of 10 to the minus 3 that is a bit adaptive during the epochs. And these are the loss functions that we considered for each part of the architecture. These are the mean square error, and the final loss function is the weighted sum of the 4 loss functions, in which we chose to assign less weight to the forward operator, because in this work we are not so interested in the forward operator. These are the results that we obtain at the end of after the training of this architecture. Again, you can see results related to temperature, water vapor, ozone, and surface spectral emissivity. And you can see represented with solid line the mean bias error, and with dashed line the mean bias error plus minus the mean absolute error, as we did before. And again, from this plot, you can see that the method is unbiased, because this is an average result as before on the entire test set. And this picture shows instead the results for a single case. In the upper part of the picture, you can see plotted the predicted values in blue and the true values in orange. And at the bottom, you can see the differences in black. And this is for the clear sky variables, and we can say that the results are quite good. But if we look at cloud variables, like the contents and the radius, we have some problems. In fact, those variables are very hard to retrieve. And so we need to add something more to our architecture. And so what we did is to consider 4 additional feed-forward neural network, very simple, with 2 hidden layers and activation function linear plus soft plus that avoids discontinuity. And we give as an input to this network the contents previously retrieved and the radius previously retrieved, and also some other variables that are variables physically related to clouds, like temperature, water vapor, and pressure. And the output of these networks will be the corrected value of contents and radius. And the loss function is, again, the sum of the four mean square error related to the 4 fit-for-1 error network. And in the loss function, we also added this term that is a sort of penalty term, a consistency term, in which we force the network to learn the physical consistency between radius and content, because we noticed, as you can see later in the plots, that in some atmospheric layers we obtain like contents that are greater than 0 with corresponding radius 0, or vice versa, that is physically inconsistent. So we add this part to the loss function in order to force the network to learn physics. And so we trained the network with Adam Optimizer, and we managed at the end to solve all the physical inconsistencies, both in the training set and in the test set. And this is a slide, a picture in which you can see the results before the additional networks and after the additional networks. You can see the liquid water content, ice water content, liquid particle radius and ice particle radius, and again, the predicted values in blue and the true values in orange. And as I said before, you can see that there are some physical inconsistencies. For example, here, where we have like ice water content 0, but ice water particle greater than 0, and we managed to solve this problem after the correction. So we still need to improve the accuracy of the values for the cloud variables, but at least we managed to solve the physical inconsistencies. So again, the strength of the method is the speed, the computational time. The training took like some hour in a standard laptop, and the second phase instead even less, some minutes. And in order to test almost 500 cases in the test set and obtain all the variables, the method takes like about 0.21 seconds. An additional analysis that we did is to compute the total cloud optical depth at 900 centimeters to the -1, starting from the retrieved cloud variables. And here in the plot, you can see a scatter plot in logarithmic scale, in which on the x-axis you can see the reference optical depth, and on the y-axis the retrieved one. So this is like the previous results. So we still need to improve the accuracy, but we are on the right way. And we then used this retrieved optical depth in order to test the capability of the architecture to distinguish between some categories. For example, distinguish between clear and cloudy scene, and using a threshold for cloud optical depth of 0.03. And the method reaches an accuracy of almost 95% that is competitive with methods that are in literature. And instead, for the 3 classes categorization, like distinguishing between clear sky, thin clouds, or thick clouds, the method achieves an accuracy of almost 83%. An additional analysis that we performed is to evaluate the capability of the method to capture the position of the clouds. So the idea behind this analysis is to consider the variables as signals. So we compute the Fourier sine series coefficients for cloud contents and radius, and we normalize the results, and then we compute the cosine similarity between the vectors. And in this way, we reached a cosine similarity of 0.667 for the ice variables and 0.73 for the liquid variables. That means that in general, the architecture is able to understand the position of the clouds and the vertical structure. So to sum up this part, what we present is a latent space, a latent twin architecture that to reconstruct atmospheric profiles and cloud variables. We need to add some additional networks in order to improve the physics behind the architecture. And we also got good results in the scene recognition with respect to results in literature and also in cloud type recognition, let's say. And the retrievals are instantaneous, so are good also for real-time application and also to understand the position of the clouds. So we need to improve a lot this architecture. And what I would like to tell you very briefly is that there is an ongoing work with the University of Bologna and Institute of another institute of CNR and the University of Florence, in which we are trying to apply the same architecture to real data. In particular, we are considering ESA data. And the architecture is a bit different, in which we more or less the scheme is the same, but we introduce like denoiser autoencoder at the beginning in order also to learn the noise of the measurements. And we are obtaining quite good results. We are testing the architecture, as I said, on synthetic ESA measurements and also real data. And in this picture, you can see, for example, the results that we obtain when we take the retrieved quantities, we recompute the radiances using our forward model, the sigma, and we plot the residuals that we obtain with the difference between the simulated radiances and the one reconstructed from the retrieval variables in black, with the variance highlighted in gray. And the red part is the noise of the instrument, in this case a ESA noise. So this is a promising work, I guess, and this is in clear sky. So we would like to improve a lot this work, also including some studies about the error, the robustness of the architecture, and error characterization in general. So let's move on to the last part of the presentation. I don't know if I don't have so much time, sorry. Okay, I'll go very, very fast. So I'm quite new in the field of data assimilation, so I'm trying to learn. But what I'm trying to do is to use forum simulated measurements and try to choose a channel to study a channel selection algorithm. So in general, as you all know, assimilating a full spectrum in NWP is very expensive under the computational point of view. So what we want to do is to reduce the amount of channels from forum and like study which one are eliminate the ones that are redundant without losing information. So this study is focused on forum, and we are, again, applying the methodology also to ESA data, and because we would like to compare our procedure with the existing ones in literature. And our focus is on surface temperature, air temperature, and water vapor. So before starting studying the algorithm, we did a sort of pre-screening. In fact, we avoid all the gas contamination, for example, O3, N2O, CH4, CO2, and COO. And we did it like considering for each of these gas the climatological standard deviation, and then we discard all the channel in which the product between the Jacobian of the radiance with respect to that gas and the standard deviation, the climatological standard deviation, is greater than the instrumental noise. And in the spectrum, in the picture, you can see the channels that we discarded for Forum, the ones that outside the Nesr bands. And after the pre-screening, we computed the weighting functions, the derivatives of the transmittances, and then we applied the Macmillan and Goldberg algorithm at each atmospheric level. The algorithm, you probably already know very quickly, consists in choosing the channel that has the highest standard deviation. After that, we choose a threshold, and then we discard all the channels that are correlated to the lead channel more than the chosen threshold. And so on. After eliminating a subset of channels, we consider in the remaining ones, the one with the highest standard deviation, and so on until the convergence. So in this way, we obtain a subset of channels that are not correlated in order to avoid the redundancy of information. And we perform this algorithm at each level, and then we unify all the results. In this picture, you can see the results that we obtained with different thresholds, and on a data set of 80 clear sky scenarios, and from the NWP SAF, from EasyMWF, and we used again our radiative transfer model to simulate the radiances, and we skipped all the information above 200 hectopascal. So as you can see, the higher is the threshold, the more is the quantity of the selected channel. And in order to understand the accuracy of the results and to evaluate how much information we lost, we use the optimal estimation framework, and we compute the covariance matrices. First, the full covariance matrices, the one using all the channels, and then secondly, we compute the covariance matrix that we can obtain using the subset of selected channels. Both the matrices have the same dimensions, so in order to perform a sort of error analysis, we compare the element of the diagonal of these two covariance matrices. And in this slide, you can see the results, the diagonal of the matrices, so the error for surface temperature, and water vapor, and for different thresholds, 0.9, 0.8, 0.6, and 0.1. And this is an indication. This indicates the error with respect to the chosen channels. And so we tested the algorithm of synthetic data for Forum and YASI, and what we would like to do now is to compare the results with other methods that are in literature for YASI, and we would like also, hopefully, to assimilate Forum radiances in MPAS using the selected channels. So to conclude everything, I show you the two retrieval methods, one that works in clear sky and another one in all sky, to retrieve the atmospheric profiles and also cloud variables and surface temperature and surface spectral emissivity. And I show you also an algorithm that we are testing to select a subset of Forum channels. What we would like to do is to add some physical constraints to our method, test the method to real measurements. And another thing that we would like to do is to speed up also the forward operator using similar approaches that we didn't explore. And we would like also to investigate other channel selection algorithms, taking into account also the instrumental error. And my work here in this mount hopefully, will be to produce the CRTM coefficient to simulate forum measurements, and also study and evaluate the eventual integration of our radiative transfer model, or maybe another one based on AI, or into your MPAS model. Thank you.
Okay, I think this is turned on. We have time for some questions. I won't throw it from that far.
Very nice talk, thank you. Very interesting. I have many questions, so I want to follow up with you later.
Okay.
I'll just ask you one here for the sake of time. Mainly about the uncertainty and the error, estimation. So especially when I couldn't really understand when you talked about the clear sky versus cloudy sky based on the cloud optical thickness, right? As far as I understand, the optical properties for cloud and aerosols are one of the most uncertain components.
Yeah.
So I'm not really sure how you came up with that approach and how much uncertainty you can, introduce by doing that, categorizing.
Yeah, the first method that I show you, I didn't test it on all sky, so I don't know. It works only on clear sky, and maybe I will test it also in clear sky, but I think it will take a lot of time because of the regularization part and the optimal regularization parameters computation. Instead, in the second one, as already said, we are testing the same architecture in clear sky that works really well and better. In fact, the cloud variables are the hardest to reconstruct, and we would like. So we didn't perform an error analysis because, as you know, in AI techniques, it's always difficult to provide an error characterization with the solution. But we would like to try some bootstrap techniques. So we would like to train the network on different training sets, changing a bit, perturbing the profiles, and then analyze the difference on the results. That's an idea, but there are so many things that we could do. So.
Right. Thank you.
You're welcome.
I have a question about the autoencoder part. So the architecture is sort of two autoencoders that are coupled together at the latent level.
Yeah.
Could you give me some intuition for why that's the right thing to do?
That's a math paper published about it. It's called the Latent Twins Framework. And in that paper, you can see a proof that learning all the architecture together is more effective with respect to learning some pieces. But maybe you mean why we are using this kind of, I don't know if I got the question.
I guess I'm asking, you could have an encoder that takes X and Y and outputs X and Y. That would sort of encompass this architecture. So I'm wondering why this specialization is useful.
I think that using the latent space and then the mapping between them, it's kind of introducing a sort of regularization, because in the latent space, the architecture is learning some physics. It's like introducing information from climatology, because in the latent space, the network learns the most important features of the variables. So I think that's because it works.
Okay, thanks.
You're welcome.
Okay. Other questions? All right. If not, let's thank Cristina one more time.
Thank you.